Hi, this is Abhilash Majumdar, a research scientist from Morgan Stanley, previously an NLP engineer for HSBC. I also maintain Google research on the language repositories like BERT and Albert. And I have been mentoring professionals and students on deep learning, NLP, and AI for organizations like Udacity, Udemy, Upgrad. So I have quite an experience in this field of mentoring. So you can find the details to connect with me in the description. Also, welcome to Co-Learning Lounge YouTube channel. So in this channel, in today's session, we're going to learn about long short-term memories, or LSTMs in short. We will also see how LSTM avoids or alleviates the drawbacks of recurrent neural networks. And we will be exploring gated recurrent units, or GRUs in short form. Please subscribe to this channel because we are going to discuss lots of interesting topics in the next few tutorials, ranging from encoder decoders to transformers, BERT, and GPT. So let's get started with this session. So the problem in the case of long-term dependencies, which is in the case called as vanishing gradients in recurrent neural networks, it comes from the fact that in recurrent neural networks, as the chain rule or the chain rule equation or differentiation of the gradients increases, the gradient change becomes significantly smaller. And this becomes a problem for general supervised learning because the weights are not getting updated in that case. So this can be understood like if you have a very long sentence, in this sentence given over here, I grew up in France and I speak fluent French. In this case, the RNN will not be able to store a lot of information. Suppose French is related to France, that particular context may not be picked up by RNN due to this vanishing gradient problem. And this is the main reason for drawbacks for the RNNs. And to alleviate this, a new kind of architecture, which is known as long short-term memories, came into the picture. This, in theory, RNNs are absolutely capable of handling, short-term dependencies. But when we come to long-term dependencies, like really large sentences or contexts, it becomes very difficult for the RNN to retrieve certain context from the sentences, as well as classify the sentiment of a particular sentence or a paragraph in general. So this was studied extensively by Yoshua Bengio et al. And Hawkrider. And they found some pretty fundamental reasons why this drawback of RNN is present. And this was quite a difficult task. And when Hawkrider and Schmidhuber actually in 1997, they came up with the idea of LSTMs, that is a special kind of RNNs capable of learning very long-term dependencies. Now, internally, the architecture of LSTM is a bit modified as compared to RNNs, as they have certain kinds of gate mechanisms. LSTMs are explicitly designed to avoid the long-term dependency problem. Remembering information for long periods of time is practically their default behavior. So all the recurrent neural networks that we see, which suffer this problem of remembering long sequences, that gets alleviated in this. So in standard RNNs or character level or word level RNNs that we saw previously, the repeating module will have a very simple structure where we have a tanh activated internal layer or a hidden layer, and the output is received by the softmax activation of the hidden layer, which we saw in the last section in RNNs. Now, LSTMs have a similar chain structure, very much similar to RNNs, but internally they have different mechanisms which are operating simultaneously one after the other. So there are sigmoid activations, there are tanh activations, and there are some internal single neural networks which are present inside the LSTM cell or an LSTM unit. And particularly, there are four single neural network layers which are interacting in a very special way. So when we move forward, we want to make sure of certain notations which are present in this blog. Neural network layer is designated by the yellow colored rectangle, and the circular pink block, this is called as the pointwise operation. Generally, this means a particular pointwise multiplication product. Then we have a single arrow which refers to vector transfer. This means that we are just passing the vector or passing the sequence of decimal numbers or tensors as it is without any modification. Concatenation means that we are concatenating 2-3 different inputs for a particular activation unit or a particular layer. And copy means we, from a particular output of a particular cell or an activation unit, we are taking 2-3 branches out of it. So with this in mind, so let's get to know about the core idea behind LSTMs. The key to LSTM is the cell state. The cell state is actually very much similar to a conveyor belt as it transfers information from one cell to the other. So in this diagram that you see, the highlighted black straight line starting from CT-1 to CT gives the cell state for a particular LSTM cell. Now, in LSTMs, the similar concept of RNNs comes into the picture, which is time dependency. So CT-1 serves as the input for the current LSTM cell, and the outputs gets transmitted as CT. So this is one of the most important output cells apart from the hidden cell, so a hidden output cell, which we will come to later. So the cell state is kind of a conveyor belt, as I mentioned. It runs straight down the entire chain with only some nonlinear activation units or activation interactions. So as we will progress, we will see that there are many nonlinear activation interactions which are coming into this picture. So the LSTM does have the ability to remove or add information to the cell state. These are also done by sophisticated activation units like sigmoid activation, tanh activations, and these are called as gates. Gates are a concept which is intrinsically very important to LSTMs because they optionally let information towards particular blocks or particular cells. They are composed of sigmoid neural networks and pointwise multiplication operation. Pointwise multiplication, as I mentioned, it is just multiplying any tensors in a pointwise manner. The sigmoid layer outputs numbers between zeros and ones. And as we know, it's an S-shaped curve. And this component allows, what kind of values or what kind of tensor values or decimal values do we want to pass to the next layer. Now, step by step, if we want to go through the LSTM, so the first step is to decide what information we are going to throw away from the cell state. Because in most of the cases, as in the case of RNNs, the input consists of two features, the XT, that is the input feature, as well as the HT-1, that is the hidden cell state from the previous timestamp. It looks like HT-1 and XT, and the output of the number is collected after passing the combined HT-1 and XT through a sigmoid function or sigmoid activation function. Now the sigmoid clamps it between 0 and 1. And this is given by this equation over here, which we can see that Ft is given by sigma of the weight, that is WFT, given into the HT-1 XT tensor. This is a combined concatenated tensor that we're passing to the LSTM cell, plus the bias, that is the bias function. Now, if we go back to our example of a language model trying to do NSP or next sentence prediction or next word prediction or even next character prediction, so this is where the most important part comes into the picture, because the sigmoid generally outputs between 0 and 1. So automatically all the redundant information are clamped and are not passed through if we pass a certain threshold value, right? So in such a problem, the cell state might include the gender of the present subject, so that correct pronouns also can be used, a very important point for co-reference resolution. Now, when we see a new subject, we want to forget the gender of the old subject. Now, the next step after, this is actually the first step, and this is, this is the first step. And the next step is to decide what new information that we have collected through the sigmoid activated unit are going to pass to the next single neural network layer. Now, this has two parts. First, the sigmoid layer is called the input gate layer, right? So what we saw over here is an input gate layer, and this decides which values we are going to update. Now we have done the first part where we have abstracted certain outputs from the initial XT and HT-1. And now we are going to further modify these values by passing it to the input gate layer. Next, a tanh layer comes into the picture. So the input gate layer is nothing but this sigma activated path, or the sigmoid activated path that we see. Now, this is actually placed to have another layer of modification of the input features from the previous timestamp. Now, the tanh is another very important function which is present inside the LSTM because it holds memory. As I mentioned in the last video, tanh has a very important mathematical property because the second gradient of tanh does not die down very easily. So tanh creates a vector of new candidate values, which is given by C cap T. Now that could be added to the cell state. Now this can be added together. That means the IT that we saw, IT means the modification of the weights by applying a sigmoid activation on the weights, given multiplied by the concatenated tuple or the concatenated tensor comprising of ht-1 and xt plus the bias. So this is our input gate. And then we have this tanh activated gate comprising where we pass this input function, where we pass this sophisticated ht-1 and xt concatenated tuple. So we can see that C cap T is given by tanh of WC given times the concatenated tensor, that is ht-1 and xt, that is the input, plus BC. This can be seen from the figure as well, because this ht-1 is first passed through the sigmoid, and the xt-1 is also passed through the sigmoid, and then they are also passed as inputs to the tanh activation layer. So in this way, the input gate is actually, collects information and stores information, like selective information, and prunes out noise or any other redundant information from the cells. Now, now we go to the next step. The next step is time to update the CT-1, that is the previous cell state, because we already have C cap T, which we got from the tanh activation. Now we have to update CT-1, that is the previous cell state, into the new cell state. Now this is done by multiplying the old state by FT and forgetting all the things that we decided to forget earlier. Now this is a very important method, because if we want to prune out, or if we want to throw out any redundant information or noise that comes into our analysis of the internal tensor, of the internal layers, neural network layers, then this particular phase or this particular gate does this for us. So when we multiply the old state by FT, we are effectively we are effectively deciding what we want to forget, or what the neural network or what the LSTM wants to forget. Then we add the IT multiplied by the C cap T. So we have the IT multiplied by the C cap T. Now this gives a new cell state, that is the CT. So by this equation that comes over here, we can see that CT is given by FT times CT-1. This allows you to disregard or throw any redundant information from the previous cell state which comes into the play. And then we are adding IT times C cap T. Now this is the same sigmoid and tanh activated internal input gates. So we are adding the input gates for the current LSTM cell, and we are disregarding or throwing away redundant information or noise which are coming from the previous cell state. So as we can see in the figure that we have, so FT comes from here, and CT-1 gets, this is a pointwise multiplication of the tensors that is happening in this context. And then we are passing it to the next part. So in that case, we have IT into C cap T over here, which again gets added. Now this is actually a different kind of concatenation where we are appending the results one after the other. And then this particular conveyor belt line, which we mentioned before, this contains the cell state, that is CT-1. It gets transferred to CT, that is the current cell state. Okay. Now this particular gate is another layer where updates the cell state. Now finally, we need to decide what we are going to output. So as of now, we have first decided the LSTM. We have first taken out the redundant information which are coming into the LSTM cell. We have pruned out the noise by passing it through the input cell layer, input cell gate. We have taken the sigmoid and the tanh activations of it. And then we're updating the previous cell state, that is CT-1, to the current cell state. Well, how we are doing that? We are removing the redundant information by multiplying FT with CT-1, and we are adding the current cell state or current cell input or the tanh activated input with the C cap T, right? And now, finally, we need to decide what we are going to output, what the LSTM cell is effectively going to output. Now, this output will be based on our cell state, but will be a filtered version. Now, we are going to apply a filter on our CT. So first, the initial step is that we apply a sigmoid, which parts of the cell are going to output. Now, this is a very important layer because the sigmoid effectively prunes out or acts as a filter, because it prunes out certain probabilistic values that we are going to disregard in our output case, in our present cell output. Then we put the cell through a tanh activation. Now, this is a very important step again, because to push the values too far between -1 to 1, This is actually a kind of a segregator function where we actually normalize the distributions for the outputs of a sigmoid cell to have between -1 and 1. So it becomes uniform distribution, and so that the memory retention becomes more. And now this particular cell is better known as the output cell, because see, the HT-1 and XT are combining here, and this is passed on again as the sigmoid, because we are again pruning some parts of the noise or input. And then we are taking the output from the CT, that is the current cell state output. We are applying a tanh activation on the CT, and then we are concatenating these two inputs to produce the HT. Now this is called as the hidden cell state, hidden LSTM cell state for the current timestamp. So this is a very important step because it contains a final or a filtered pruned output. So if we summarize the steps, what is going on? So initially we have an input gate where we are trying to prune out certain redundant information. So we get the HT-1 and XT concatenated tuple together. We multiply it with a weight matrix, right? And coupled with a bias. And we pass it to the sigmoid. The sigmoid has a very important property because of its clamping nature. Between 0 to 1, it prunes out certain redundant information from it. And the next step is effectively trying to again apply a filter on this, and by applying another sigmoid function that we see over here, that is the input gate, sigmoid times Wi multiplied by this tuple HT-1 comma XT plus the bias. And we are having an additional tanh activation layer because this actually allows you to modify the cell state. Now this comprised value gives you the input gate layer or the input gate cell. Right. Now the next part is to update the old cell state, that is CT-1, to the new cell state, that is CT. So this can be done by applying a forget gate. So the forget gate actually helps you to remove or prune out certain noise from the cell, as well as add the current important information from the current LSTM cell, not from the previous LSTM cell, but for the current LSTM cell. So this is done with the help of the FT multiplied by CT-1. Now the forget is done by in the first step that we saw over here, which is given by this equation. This FT is multiplied with CT-1 and it is added with IT times C cap T. Now IT times C cap T is got from the input gate. So the first step is the forget gate. Then we have the input gate. Then we have the still state gate, which updates the cell. And finally, we have the output gate. So the output gate, again, it contains a final filter on the CT, or that is the output cell. So because we want this, because we want to produce the HT also, hidden cell state, for the current LSTM cell, right? Because this will again be fed to HT+1, that is the next LSTM cell that is going to be present after it. So in this case, we apply a sigmoid activation with the weights on the combined tuple that we see, HT-1 and the XT, that is the input vector, plus the bias, right? And then we are concatenating the CT, the tanh activation of the CT and the input gate, that is the OT. And then we are passing it through this HT. So comprisingly, these four steps which are present, these four gates which are present in LSTM makes it, very structured and very architecturally sound when we want to cover very large sequences of sentences or large phrases. So the forget gate removes certain redundant features and acts as the first filtering mechanism for the inputs. The input cell gate actually allows you to have a proper input for the cell for further modification and also updating the cell values for the current time step. The cell gate actually modifies the value of the current time step by applying certain filters, by removing redundant noises. And then we have the output cell. The output cell is again another concatenation layer of a tanh activated cell output and the hidden input to produce the HT, that is the hidden output for the current LSTM cell. So these four steps are very, very important for a particular function to function, for an LSTM to function particularly properly. So there are again variants of long short-term memories, which are very detailed and very fine-tuned. So LSTMs, regardless of their operation, is actually one of the building blocks of all the transformer architectures that we see nowadays, because LSTMs have this beautiful property of memory retention and holding information for text sequences, long text sequences for a longer time span. And because of this tiny activation in the intermediate cells on intermediate neural networks inside the LSTM cell, the CT and the HT dependencies for large text also get sampled very easily and sampled very properly. So this is why the LSTM is a very important aspect when it comes to any NLP tasks, as well as sequence modeling or text generation. Particularly in the case of text generation, LSTMs function really well as compared to RNNs. So there are other variants of LSTM. So, but not all LSTMs are the same. In fact, most of them are derived from the standard LSTM that we see. So one of the most popular versions of LSTM is the peephole mechanism. Now, this means that we are letting the gate layers look at the cell state. What does this mean is that we have the normal LSTM cell that we saw over here, this normal picture that we see here. Now, additionally, we are also adding the cell state to look into the input features at the start and also in the intermediate part. So we can see that the cell state, that is CT minus 1, is also added to the sigmoid activation function. Now, why this is important? Because in this way, this gate layers also look at the cell state. So this allows pruning from the previous cell state as well. So remember, the sigmoid function is very important for pruning out certain information from redundant information, because it clamps between 0 and 1. When we are adding CT minus 1, we are adding more information to be pruned out. So in this case, you have a concatenated output or an input vector, CT minus 1, that is the previous cell state, the HT minus 1, that is the previous hidden state, and XT, that is the current input feature, and the bias. So this is the modification for creating a peephole movement. So, and this is very important when we want to fine tune, or when you want to fine tune an LSTM cell to gather more information or hold more information. There are other variant of LSTM as well, which is known as a gated recurrent unit. A gated recurrent unit, or a GRU, was introduced by Cho et al. So it combines the forget gates and the input gates into a single update gate. So instead of having 4 different gates, which are mentioned in LSTM, that is the input gate, forget gate, cell gate, and the output gate. So there is only, it combines the forget and the input gates into a single update gate. So it merges the cell state and the hidden state, that is the CT minus 1 and the HT minus 1, CT or HT for the current timestamp. It also merges that, and it also makes some other changes. The resulting model is very much like this. Now, GRUs apply this performance enhancement because most of the information that is being left out by the sigmoid, or that is being left out by the tanh activation, is effectively fine-tuned or cleared by combining the different layers of the cell. So if you can see the ZT is given by the combined nature of the input and the forget gates. That is the first two steps of an LSTM network. So this is given by the sigma times, that is the sigmoid activation of WZ, that is the weight vector, and the combined tuple, that is the input tuple, HT minus 1, XT. And then we have the RT, right? The RT is again a combined version of the input tuple. Now, H cap T is effectively the C cap T that we see, right, in LSTMs. So in LSTMs, we have this C cap T, which we saw earlier. Now, this H cap T is very similar to that. So it applies RT with respect to HT minus 1. It concatenates that with XT. And then we have HT. This is the standard output gate. Now, if we see, it also merges the cell state and the hidden state. So you are getting only one output out of this. So you can see over here that HT is getting outputted both as the cell state as well as the hidden state. The cell state is transferred straight like a conveyor belt. The hidden state goes up. So there is a branching of the outputs which takes place. So effectively, the GRU only outputs a single point, that is a merged cell state and the hidden state. And it does this by 1 minus ZT times, by applying 1 minus ZT times HT minus 1 plus ZT into H cap T. So H cap T is the tanh activated cell, and the ZT is the first input gate cell, which is also the forget gate, because in the case of GRUs, they are both merged. So this is effectively one of the few modifications of LSTM variants. There are other modifications as well, like depth gated RNNs. And there are modifications which are related to CUDA versions as well for NVIDIA. But effectively, the base or the modern architecture of LSTMs consists of these 4 different layers. That is the input gate, the forget gate, the cell gate, and the output gate. So effectively, this is how the LSTM actually performs. And effectively, that is what I all wanted to cover. And due to this, it is very important point to remember that the drawbacks of RNN, which was vanishing gradients, and there is another problem of RNN called as exploding gradients. These are effectively solved with the help of LSTMs, because LSTMs have this interesting property of having internal single neural networks, which are effectively very useful for holding information and effectively collecting information for longer sequences of text and corpuses. So that was all that I had to cover, and I will see you guys in the next video tutorial. Thank you.